Okay, let me welcome you to this lecture 11 of our course on reinforcement learning at ASU. So far, we have discussed approximation value space, and the main algorithms have been value iteration, policy iteration, rollout, and approximations thereof. Today, we are going to talk about some new methods that we haven't encountered in any detail before. One is linear programming. There are three exact methods for solving dynamic programming problems over an infinite horizon. Value iteration and policy iteration are the first two, and there's a third method based on linear programming. And it hasn't received so much attention in reinforcement learning, but it has some interesting possibilities, particularly because it can be implemented in approximate form using approximation architectures. So we are going to discuss briefly this method, and then we are going to focus on approximation in policy space. Approximation in value space sits at the one end of the spectrum of methods in reinforcement learning. The other end is approximation in policy space, where instead of approximating and training value functions or cost functions, we train and approximate policies using data. And we are going to discuss various methods that are used in the context of approximation policy space. Policy gradient methods and random search methods. Both of these are popular, particularly policy gradient. And we're going to spend most of our time in this lecture talking about them. So I'm going to go to videos. We have several videos that we're going to use in this lecture, so I'm going to go in the first one now. First topic is linear programming. And by the way, I'm going to switch, after this outline, I'm going to switch to a video lecture from the 2019 offering of the course. Linear programming is another interesting method for solving dynamic programming problems exactly or approximately. It's an alternative to approximation in value space and approximation in policy space, but it has not reached the popularity of these methods. Nonetheless, I think it's interesting, and I'd like to mention it. One of its limitations is that it doesn't go well with neural networks. It requires a linear approximation architecture. Then we're going to switch to approximation in policy space. And I'm going to describe various contexts within which this approach it might be preferable than approximation in value space. Of course, here what we're trying to do is obtain parametric forms of policies to use online. And we obtain these parametric forms by training. And there are a number of different methods for training. One is a possibility that's based on cost optimization, which we're going to focus. And it uses random search methods. Another possibility is to use what's called policy gradient methods. Both of these are quite popular. And we're going to take a closer look and then discuss some of their, let's discuss some approximation, some implementation issues, and also some of their advantages and drawbacks. So I am now going to switch to the video. Okay, so here's a key idea. Let's consider discounted infinite horizon problems. The optimal cost function is J star. It's an n-dimensional vector. And the idea here is that J star is the largest vector J that satisfies this constraint here. Okay, let's look at this constraint. First of all, this constraint is linear in the vector J, right? and there's one constraint for every state and for every control. Okay? So there's a large number of linear constraints that specify a polyhedron in J space. And the claim is that J star, the optimal cost vector, maximizes the sum of the components of J. There could be also other positive coefficients here. It's again the approach to legitimate. And J star maximizes this linear expression subject to these linear constraints. So J star can be obtained by solving this linear program according to this claim. Now let's try to visualize this result. Okay, this figure here involves two states and two controls. Two states, so J is a two-dimensional vector, J1, J2. So vectors J live in here, okay? Now let's look at an inequality of this type. Let's look at the inequality involving I equals to 1 and control U1, okay? State 1, control 1. And this hyperplane, the hyperplane defines a line, okay? And the vectors that satisfy this inequality are on the green side of this line, okay? So this first inequality cuts off this part of the space. The second inequality corresponds to state 1, control 2, okay? It's a line like that, and everything that lies on the green side satisfies the corresponding inequality. Let's go now to state 2, control 1, another hyperplane, and this green side is the feasible portion defined by the inequality, and we have that one also. So the feasible set of this linear program is this green polyhedron here. And what we claim is that there is a northeast corner to this polyhedron, which is exactly J star. It's a pointed corner. And therefore, if I maximize the set of the components of J, which is like pushing this hyperplane all the way towards the corner, I'm going to find J star. The hyperplane could be slanted also, which correspond to different weights on these components. This is really just the point. So if I go in this direction, I'm going to get where I want. Okay. So how do we prove that? It's two lines. We take any point J in here and we apply value iteration to it. We start value iteration from that point, okay? And I claim that value iteration is going to stay within this green polyhedron and go to J star. Why is that? Well, if J satisfies this inequality, what does this mean? That when I apply value iteration to it, I'm going to get something bigger. So the first value iterate satisfies this inequality, okay? The typical value iterate, the kth value iterate, is k iterations of value, k value iterations applied to J0. And because T is monotone, if the first inequality goes to the right, all of them go to the right. And we have this relation here. Every one of these J's is going to be moving to the northeast. And you can also see that it stays in here in the polyhedron, but that's not important. What's important is that value iteration converges to J star. Therefore, every J within this green polyhedron lies to the southwest of J star, okay? And J star also satisfies this inequality, obviously, by Bellman's equation. So J star lies on the green polyhedron, and everything else in the green polyhedron is below and to the southwest. That's the proof. So you might forget about value iteration, you might forget about policy iteration. Let's just go to your favorite linear programming software, Cplex. It's a very, very refined code. Give it the data and get the solution. That's certainly a legitimate approach, but what is the problem here? What's the difficulty?
Large number of constraints.
Large number of constraints. large number of variables too, right? N variables and as many constraints as there are state control pairs. So this approach can be applied for a limited number of states, but at some point it becomes inapplicable. So we think of approximations, but taking this linear program as our basis. Okay? So let's consider parametric approximation in value space. This is the difficulty we just mentioned, too many variables and too many constraints. Introduce a linear, that's important, a linear feature-based architecture. Okay, we introduce M features with corresponding M weights. And now we're going to try to find the weights by linear programming. A much smaller number of weight, a much smaller linear program. We replace cost vectors with parametric cost vectors, and we reduce the number of variables this way. We have a large number of constraints, but we pare them down by sampling a relatively small number of them. And we consider this approximate linear program, okay? We maximize this expression, which is linear, right? Because it's linear in R, because the parametric approximation the parametric architecture is linear. And now the constraints become like so. They are still linear because this is linear in R, this is linear in R. However, we reduce the number of variables and constraints by selecting a set of representative states and a set of representative controls. So the true number of states and controls might be huge, but somehow we reduce this number, which means that we're considering a polyhedron that's bigger, okay? Fewer constraints, bigger polyhedron for approximation. Okay, now the difficulty is here. How do you reduce the number of constraints intelligently? Well, obviously, you should enforce the constraint for the important states and the important controls, important in terms of our problem. So one possibility that's typically tried in this setting is to sample the state space and the control space by using some known suboptimal policies. You may know some good policies that look good, and you introduce representative states and controls. You're not afraid of adding more as long as you don't go overboard and add too many. And you may solve the problem and look at the results. And if that doesn't work, then you may enrich the subset as necessary. All of this, of course, involves heuristics and choices, and okay, but this is the main difficulty here. On the other hand, having chosen successfully representative states and controls, now there are no pitfalls. You give this to your linear program and it will solve it exactly. No gradient method to crap out on you, no oscillations, no exploration to deal with. All of this stuff that we have discussed goes away. Once you have selected you have reduced the constraint set appropriately, then you are in good shape. This approach has not been very popular. It has been around for 20 years now. It's not very popular, but it has been successful where it has been applied. And in my opinion, it deserves more attention. The jury is still out on this approach and what kind of problems it can address. And like I said, the main advantage, the strong point, is that capitalize on the reliability of large-scale linear programming codes. Okay, so let me just interrupt and ask for questions on this linear programming approach. Do you have any questions?
I have a question. So the parametric model, it somehow produces a reduced set of variables and a reduced set of constraints that you can just plug directly into your linear program?
That's right, yeah. Well, you use some kind of a heuristic sampling method to get the representative states and representative controls. So that reduces the number of constraints. So it's like taking the polyhedron, the feasible polyhedron of the linear program, and approximating from the outside with another polyhedron that has fewer corners. And then we solve that, and what we get is an approximation in value space. And then we have to use a one-step or multi-step look-ahead method for online play. The offline training is to solve the linear program, and then obtain the parameter vector R. Then you do online play with one-step or multi-step look-ahead. That's the approach here.
Okay, thank you.
Okay. Okay, so let's go into approximation in policy space now. I'm going to start the video. So let's talk about approximation in policy space. Excuse me just one moment. Okay, so what's the general framework? Here we parameterize policies, not costs, but policies, with a parameter vector R. So a parameterized policy is denoted by mu's of R. Each R defines a policy, okay? And the components of mu are denoted by, like so. There's one component for each state. Of course, we're dealing with stationary policies because we're still looking at infinite correlation problems and discounted problems for that matter, for the most part. Okay, so we have discussed how to parameterize cost functions, but how do we parameterize policies? Well, sometimes your problem is such that you can tell what are good, there are natural good parameterizations for policies. So that would be one thing. Another possibility is to look at feature-based architectures. And then you may also use neural networks if you don't know a feature. It's still possible to do all this. And the idea now is to choose a parametric architecture and optimize some measure of performance with respect to the parameters. So let's give a couple of examples of parameterizations. This is a problem where it's much easier to think of a control parameterization, a policy parameterization, than a cost parameterization. It comes from the general area of supply chains, inventory control. It's a very, very important type of problem in industrial engineering. Here you have, I'm giving you a simple version. We have a retail center which stores some stock of some product, and it replenishes the stock by ordering some production center. And after some delay, whatever you ordered arrives. There may be production delays, there may be transportation delays, and so on. Now, this stock is used to satisfy stochastic demand here, and the objective is, well, to have stock when you need it, because otherwise you may have to purchase it at a high price, let's say. If you run out of stock, you may have to purchase at a high price. So that's basically one cost consideration. The other cost consideration is if you order haphazardly, there may be greater cost for production. So somehow you have to smooth out your orders. There may be, and okay, there may be an upper bound on how much stock you can order. There are many complicated issues here. Generally speaking, this type of problem can be formulated as a dynamic programming problem. You look at your stock and you look at whatever else is happening here, how much you have ordered in the past, how many orders are in transit, and so on. And this becomes your state. The current stock in here, the orders in transit, and there may be also some other stuff that you can make it more complicated than that. So you can formulate by dynamic programming, but it can be very difficult to solve it exactly.
particularly if you have a more complicated system involving multiple production centers, involving assembly lines, assembling different products into other products, and so on. However, in this setting, there are some intuitive policies, type of policies that you can use. And here's an example. Here's an example of a near optimal policy. When the retail inventory goes below a certain level, when you're running low, order more, okay? With the numbers, the critical level, and the order amount being parameters. So you may set these critical numbers and then try to optimize them in a optimization policy space manner. So in fact, that's the way in many inventory systems, that's the way they work. They set critical levels, and then hopefully they work well. And if they don't, they adjust them, perhaps manually, perhaps with some algorithm. There are many heuristics around this type of policy. In some cases, this type of policy is optimal, but in other cases, it's not. But it's close to optimal often. So this is an example where there's a natural, good parameterization in policy space. Okay, here's another example. Policy parametrization through value parametrization. You may know good cost features. So you may have a linear architecture using these features for cost parametrization. And once you have this J tilde, then you can define a policy parametrization through this look-ahead minimization. So I know a good J tilde somehow because I have good features. I don't know the weights, but I stick it in there, and that defines a policy parametrization. So now we may try to find optimally the weights of the policy by using a policy optimization method. Now, when is this useful? If you know a good parameterization in value space, but you want to use a method that works well in policy space. Okay? And here's an example that I have had some personal experience with. Tetris, okay? It's a good test bed for challenging quite a few methods. Now, in Tetris, we've seen this example before. There are good features for cost parametrization that Tetris players recognize, like the height of these columns, the relative difference of the heights of adjacent columns, the number of holes in the wall, the maximum height of the wall, and so on. There may be some others too, but there's a relatively small number, like 20, 30 in that range, and these work well, and there's a good parameterization with respect to that. So we could use approximation in value space, in approximate policy iteration, and so on, but it turns out that with this policy parameterization here, people have been able to use random search and do very, very well. So this is an example where we have a good linear parameterization through features, but we use approximation in policy space and training in policy space through random search. Okay. So there's another context of using parametric approximation in policy space. So let's take an early break and think about that. Think about contexts where approximation in policy space is either essential or useful. And I've listed here 6 contexts just to consider. One we have discussed, when problems where there's a good natural policy parameterization, like the supply chain problem. Problems with good value parameterizations, where we use a good policy training method, like the Tetris problem I discussed. Okay, I think I mentioned this at some lecture in the past, approximation in policy space on top of approximation in value space to facilitate the implementation of a suboptimal policy. Another one, use policy parametrization and policy optimization to learn from a human expert or a software expert that generates good controls. You can learn from that by using some kind of training in policy space. Now, here's something that we haven't talked about. There are interesting problems that look like dynamic programming, but they don't fit neatly into the framework of dynamic programming because the information structure may be unconventional. Like, for example, there may be limited memory. We have assumed so far that the controller never forgets anything, right? Remembers the past controls, remembers the past information. But there may be some limited memory limitation. And here's another interesting context, multi-agent systems, where you have your controller distributed out in various decision points, and each decision point has its own local information that may not be shared with other agents. Like robots going around doing things, they have a common goal, but they explore their environment and they get information from the environment and they make decisions on the basis of this information, but they don't share this information with other robots because of bandwidth limitations, whatever. Or they may share it, but there may be some delay in getting the information to the other robots. Now, conventional dynamic programming breaks down in this context. So think why approximation in policy space might work in this context.
Okay, so we're actually not going to take a break, but we will continue with the next clip.
That's the first two. Policy approximation on top of value approximation. Okay, suppose that we use some kind of a training method in the trains in value space and we obtain some J tilde. Then this defines a policy, right? On the other hand, this policy may be hard to implement because you may need here the model of the system, transition probabilities, a minimization online, and so on. Approximation in policy space helps to circumvent these difficulties. How so? We approximate this mu hat by using a training set consisting of a large number of sample pairs of states and controls. We don't have to do it for every state, just for a large enough training set. And then we use approximation in policy space by introducing a parametric family mu tilde, not mu hat, mu tilde. And we try to match mu tilde to mu hat. We try to match mu tilde and its parameter to the sample controls obtained from this policy here. Okay? So this is like learning from a software expert. If you think of this as being an expert, we learn to mimic this expert by approximation in policy space. We could have also a human expert, we discussed that, who can choose a good or near optimal control US at any state I sub S. Again, we form a sample set of representative state control pairs supplied by the expert. We introduce a parametric family of policies, some mu tilde, that tries to mimic the expert. This is also called in artificial intelligence, called supervised learning. And there's a lot of literature on this type of methodology. And it has been used in the context of dynamic programming in a number of ways, in chess and backgammon. Okay, there are examples of that. Another, of course, the main difficulty with this is that you don't expect approximation in policy space to do better than the expert that you train it with. you cannot improve, you cannot expect to improve on the performance of the expert. However, this may be a good policy to use it as a starting point, to initialize some other method, a good starting point. It has been used in this, for example, AlphaGo uses this type of initialization for a more complicated method. Okay, unconventional information structures. So approximation value space is based on dynamic programming, and there the premise is that the controller has access to the exact state, or in the case of partial state information, to a belief state. However, there are contexts where this may not be true, where there is no full state or belief state available in all parts where the decisions are made. One possibility, the controller forgets information. And another possibility, another example, some control components may be chosen on the basis of different information than others, like in this multi-agent setting that I noted earlier. So we have here decision-making information gathering that is distributed among multiple autonomous agents. Each agent's action depends only on the local information. The agents may be receiving delayed information from other agents. And then conventional dynamic programming breaks down, and approximation in policy space is applicable. There are ways to use conventional dynamic programming, but a lot of the approximation value space methodology that we have discussed does not apply anymore. Another possibility, of course, in this context is to establish some kind of a center that picks up all this information from the agents and broadcasts it down. In other words, there's information sharing among these agents using a central controller. Or even the central controller may make all the decisions, collect all the information that's obtained from distributed points up to a center where all the decisions are made. And that brings us back to dynamic programming, approximation value space, and so on. But barring that, you're pretty much stuck with approximation in policy space.
Okay, so now we are going to go into algorithms for approximation in policy space. We have, what we have done so far in this area is to discuss contexts where approximation in policy space may be useful. And are there any questions on that before we go into the training of methods for approximation in policy space? Okay.
Now let's go into training by cost optimization. I'm going to restart the video. So now let's go into how do we find R? How do we find the parameters in policy parametrizations? And let's look first at random search. The general training framework that we are considering is one whereby we have our system that's driven by some kind, it involves some uncertainty, generates a state or a belief state, which is fed into a controller. Now the controller is parametrized with this R. For each R, there's a different controller, and this controller applies control, and there's cost generated. So this is the generic dynamic programming setting with approximation in policy space. Now let's look at the training, finding R by cost optimization. Every R defines a stationary policy, which we denote like so, and with these components. And we determine R by minimizing the cost corresponding to the parametrized policies. Okay, what is this? This is the cost of policy mu tilde R, starting from a selected initial state I0. So this is a function of R, the parameter vector. And we can try to find the optimal parameter vector. Okay? Of course, there's a limitation here that the initial condition, the initial state is fixed. So if you don't have a preferred initial state and you want to optimize over a variety of initial states, then you may consider a modified framework whereby you consider a probability distribution of initial states and you minimize the expected cost with different initial states weighted according to these probabilities here. So this is the case where you have a single initial state. This is the case where you have multiple initial states and you take an average between them. Okay, so now the key question is how do you solve this problem and how do you solve this problem? That's the training problem. So let's look at random search. Random search is quite a large and widely used methodology, and it applies to general minimization problems of this form. Minimize a cost function of R, a generic cost function, subject to R being in some constrained set. And of course, this F here may involve an expectation, or it may involve something a lot more complicated than it appears here. Random search methods are iterative. They generate a parameter sequence, always aiming at cost reduction, looking for better and better cost, but exploring at random around the current point. Given the current point Rk, we generate randomly points in a neighborhood of Rk, and then we choose some new point with this neighborhood that hopefully is better or is more promising, and then we keep going. More random points, move forward, and so on. This is a typical fashion. Neighborhood search with the points within the neighborhood generated in some random fashion. There are quite a few methods of this type, and they generally have good convergence properties. In other words, you'll see theorems that given a sufficient number of random points, you can get arbitrarily close to the optimal solution. However, in practice, they tend to be slow. An advantage that they have is they don't care about local minima. Okay, they're not affected as much. Gradient type methods are affected by local minima. These are not affected that much. In other words, in theory, this method can find the global optimum, approximate the global optimum arbitrarily closely, given a sufficiently large number of random points or iterations. They don't require a differentiable cost function either. Anything goes here, actually. There are adaptations of this method for discrete space, for a continuous space, for non-differentiable cost functions, and so on. And let me give you some examples of methods like that you may have heard. Evolutionary programming. Okay, there's a large methodology with some theory and a lot of heuristics. Taboo search is very popular in operations research. Simulate annealing is another methodology that you may have heard of. It has an interesting theory, but it has the same limitations as some of the others. And finally, this cross-entropy method that I'm going to discuss briefly here to give you an idea of how these methods work. Okay, remember that we want to solve this generic problem. And we don't care if it comes from dynamic programming or not. This is generic. And here is how cross-entropy works. Remember, like all random search methods, it generates a sequence of iterates, right? Rk, and then Rk plus 1, Rk plus 2, and so on. And at the current iterate, it constructs an ellipsoid, which I denote here by Ek, which is centered at the current iterate. Okay. This is the neighborhood within which we search. We generate a number of random samples within this ellipsoid, and some of them are going to be good, some of them not so good in terms of cost. Now, this method accepts a subset of the samples that have low cost, and these are the green ones in this figure. So within this ellipsoid, I generate all these points, the black ones and the green ones, and I select a portion of those that have low cost. And now I can generate the sample mean of these accepted samples. The sample mean, okay, sample mean in the usual way, and that I call RK plus 1. So I generate the good points, I go towards the good area, and I go right in the middle of those. Okay, that's my RK plus 1. And then I have to generate a new neighborhood, and for this, I look at the shape of this region here. So I look at the sample variance or the sample covariance of these green samples, and it defines an ellipsoid. Now, this ellipsoid will encircle those green points, but I want to make it bigger. So I look at a bigger ellipsoid with the same shape as the one defined by the sample covariance. And now I generate new points here, delineate the green samples, move to the middle, and keep going like that. Okay, so let me repeat. We construct a sample covariance matrix of the accepted samples, and form the new ellipsoid using this matrix, and continue. How does this method work in theory? Okay, it has, okay, there is a substantial theory actually here, some of it based on probability theory, some of it based on statistical concepts. And however, the guarantees on rate of convergence are limited. This method can be very slow. Oftentimes, domain-specific insight can be very helpful, heuristics and so on, like a lot of these methods. However, it's very simple. It's very simple to implement. All you need is to be able to calculate function values, basically, right? You need function values to be able to delineate the green points from the black points. And that's all you need. And some elementary software here that you have to write for ellipsoids and so on. Moreover, it's very well suited to parallel computation. Why is that? Because these points can be generated and evaluated in parallel, right? So that's easy. And there's an interesting point of view here. This method resembles the gradient type of methods that we have been discussing. Why is that? Why does it may look like a gradient method? What is common with gradient methods? Well, what do gradient methods? Yeah, go ahead. Go ahead, please. Yeah, it's looking for better points. Like the gradient method is iterative, again, generates a sequence RK, and calculates a direction for better points, okay? And it moves along that direction, aims for lower cost. Similarly here, we look at sort of a direction for better points, but what is better is evaluated by sampling as opposed to calculating a gradient. Okay? Yeah.
Okay, that's the end of this video. And we are going to take a 15-minute break. And we're going to come back for a longer session with 2 more videos. Are there any questions before we go into the break? Okay, so we're coming back in 15 minutes exactly. Okay, we're getting ready to start. The remainder of this lecture is going to be on policy gradient methods, and I'm going to start the video now.
I'm going to go now into policy gradient methods. It's our last topic here. Okay, here, instead of using some kind of a randomized gradient, we look at gradient, real gradient. In particular, Remember that we parameterize policies with parameter vector R. We consider the cost of the policy for a given initial condition. And let's focus for a fixed initial condition for the moment. And we apply the gradient method. This is gamma k is a step size. This is the gradient of this function of R. Okay, this is a function of R. And we take the gradient with respect to R of this function. And we have to assume that this function is differentiable with respect to R, so that the gradient exists. Now, the main difficulty with this approach is that this gradient may not be explicitly available. To differentiate a dynamic programming infinite horizon discounted cost with respect to a parameter is just cannot be done. It's very difficult. So this gradient cannot be calculated you cannot write down a formula for it, and you cannot calculate it even in software exactly. The best you can do is approximate it by finite differences. So we have a parameter vector R, multidimensional. We are at a certain point Rk, and we go along the various directions and finite difference the cost to obtain the gradient. Okay. Now, if the problem is deterministic, that may not be a bad approach, okay? Because presumably costs in all directions can be calculated exactly, right? There's no randomness in deterministic problems. So finite differencing may not be a bad idea. On the other hand, when the problem is stochastic, the cost function values that you need to difference must be computed through Monte Carlo simulation. And then Monte Carlo noise comes into play, and you need a gigantic number of samples to get accurate enough gradients that are usable in this algorithm. So that's the main problem with stochastic dynamic programming and gradient optimization. The gradients are not available, and they're hard to approximate by Monte Carlo. However, there has been a clever get-around to this that applies to dynamic programming, and it's actually quite popular. To explain this, I'm going to go back to the general problem of optimization of a generic cost function f of a vector z, okay, subject to some constraint. Now, this f of z may hide in their expectations and so on, okay, but let's write it abstractly as f of z. And we take a radical step, an unusual step. We convert this perfectly deterministic problem to a stochastic problem involving an expectation. And instead of minimizing over the z vectors, we minimize over probability distributions over the z vectors. Okay? We randomize the problem, even though it's deterministic at an abstract level. Z lives in some set, constraint set z, and we consider not points in there, but probability distributions over z. Of course, the points themselves are probability distributions. They're atomic distributions. So this set of probability distributions is larger than the set z, and this minimization gives you a lower bound to this minimization, right? You minimize over more alternatives. But we view z as a random variable, and we consider probability distributions over z, and we now minimize this expected value. Okay, so what does this have to do with our infinite horizon dynamic programming? How do I randomize a dynamic programming problem? Talking about the infinite horizon discount problem. It already has some stochastics in there through the transition probabilities, but the variables of optimization, which are the controls, are deterministic. At every state, you apply a single control. Now we are going to expand this framework to consider randomized policies, whereby at a given state, we don't have a single control that we apply, but we have a probability distribution of controls, and we choose by flipping a coin with respect to that distribution. So we enlarge the set of policies to include randomized policies, mapping a state I into a probability distribution over the set of controls. And we consider optimization over randomized policies. Now, one thing to note is that in exact dynamic programming, in the problems that we have considered, discounted and stochastic shortest paths, optimization over randomized policies give you the same results as optimization over the ordinary non-randomized policies. In other words, you get the same optimal cost, and also the non-randomized optimal is also optimal for the randomized problem. Okay? So that's a theoretical result that tells you that the optimal value of this problem is the same as the optimal value of this problem. And another thing to note is what is Z in the dynamic programming context? Z is the state control trajectory, okay? So given a state control trajectory, this gives me a cost value, which is then take the expected value and we get the cost like that. So now let's go into approximations. This methodology is for exact solution, right? Now let's go into approximations where instead of optimizing over all probability distributions, we restrict attention to a parametrized subset of probability distributions. And the parameter is R. So instead of minimizing over all probability distributions, we minimize over just this parametrized subset involving the parameter R. And this becomes now a minimization over R. Okay? And we can use a gradient method for solving this problem. This is a function of R. This involves probability distribution, but still this expectations of depends on R. In other words, for every R, you get a number here, and you want to minimize over R. And this expression here as a function of R hopefully has a gradient. We assume that it has a gradient. And we generate a sequence of R vectors by going in the direction of a negative gradient, use a step size gamma k. Now, okay, so how do we calculate this gradient? That's the big question. And calculating this gradient looks very formidable, but it turns out that there's a useful formula that can be implemented in a nice and convenient algorithm. This formula involves the gradient with respect to R of the logarithm of the probability distribution. In the reinforcement learning literature, this is called the gradient trick, okay? Or I guess it's called the gradient trick, right? Yeah, and here it is. Okay, remember that we want to calculate this gradient of this cost function, and we're going to express this a little different, that involving the logarithm of this p as follows. Okay, so this is the probability distribution over which we want to optimize, and I am at the current iterate rk, and let's suppose that this is a discrete distribution, so I can write sums instead of integrals here. The gradient that I want to calculate can be written like so. This expected value is just the expected value of z with respect to these probabilities. And now, gradient of a sum is equal to the sum of the gradients. And now I multiply and divide with the probability values here. And this expression here can be recognized as the logarithm, as the gradient of the logarithm of p. So now what I have is this thing here weighted by these probabilities over z. So this is an expected value with respect to this probability distribution. So gradient of expectation has become expectation of a gradient, and in particular the expectation is with respect to the parametrized probability distribution. So now here is my algorithm that uses this formula in place of that. We are not going to calculate the gradient here and use it in the gradient formula. Instead, we're going to take just a sample. For the current IK, I'm going to take a sample of Z, and I'm going to use a sample gradient in place of the full expected value. Okay, so this is my problem. I am at RK. I obtain a sample ZK according to this distribution. In the context of dynamic programming, that corresponds to generating a trajectory that corresponds to the current R, and the current policy that corresponds to R. And I calculate this sample gradient, and I move in the direction of this sample gradient rather than in the direction of the expected value of that. And that's all. You have the policy gradient algorithm here on the board. That's all there is to it.
Okay, let me switch to a new video now.
Now we're going to go to discounted problems. Here, Z, okay, the samples are trajectories, okay? And for a given R, for a given policy, these trajectories have well-defined probability distributions, and they can be generated by Monte Carlo, okay? So we consider parametrization of randomized policies, whereby at state I, you select a probability distribution over the set of controls that depends on the parameter vector. So this is our parametrized randomized policy. And then for a given R, the state control trajectory is a random trajectory with well-defined probability distribution, which we denote by P. Okay? So remember, we have the random variable Z, the probability distribution that's parametrized by R, and samples of Z are generated by this probability distribution. Now, the cost corresponding to a trajectory is given by the standard discounted cost, and this is just a sample, okay? And the problem is to minimize the expected value of this cost over R. So that's the general form of the dynamic programming problem. And we use the gradient iteration, the sample gradient iteration from the previous slide, okay? So we have to generate this can be easily generated. For a given R, generate the sample trajectory, generate the corresponding cost. This is easy. But how do you calculate the gradient of this logarithm? Well, it turns out, again, that there's a nice formula, and it's given in red here. This thing is obtained by, okay, let me read this formula for you. I think you have to look at it for a while before you can understand it. But this involves the logarithm of the transition probabilities along the trajectory, the current trajectory that I generate. This is the logarithm of the randomized control. And we take the gradient of that at the current point RK along the trajectory. So generate trajectory. As I go, calculate these quantities here, add them up, and that gives you the sample gradient. This is the cost sample, and put them together, and it becomes actually very simple. It's very simple to program. Once you have a parametrization of the randomized controls, then typically its parametrization admits an easy gradient calculation, and it all works out just fine. Now, it doesn't scale, okay? Or it's very slow. I agree with that. It can be very, very slow, but it's very convenient and seductive, okay?
Maybe some good tricks with the approximation, some good
Again, there's a long discussion after this slide, and it's not very intelligible or interesting, So I'm going to stop the video here, and I'll come back to the slide, and I'm going to switch now to my slides as opposed to the video. So let me do that. Okay, so let me remind you of the generic method for solving approximately this generic minimization problem by using parametric approximation and replacing the minimization over z to minimization over a subclass of probability distributions that are parameter over z parameterized by RK. So what we do here is at the given point Rk, we are going to generate a new point, Rk plus 1. How do we do that? We sample we obtain a sample Zk using this distribution at the current value of parameters Rk. So now we have Zk, and we compute this gradient here that corresponds to just this sample. This is ordinarily we would like to have the expected value of this, but this would require Monte Carlo simulation. The true gradient involves the expected value of this. So we use just a sample gradient, and we have this class of probability distributions. We have Rk, we have the sample. We calculate the cost function at Zk. We calculate this logarithm and the gradient of the logarithm with respect to Rk at the sample Zk, and we use this as the incremental gradient direction. And actually, let me note one thing here. This is called gradient or policy gradients associated with gradients, but actually the gradient of f does not enter into this formula at all. That's very peculiar. What you have instead is the gradient of the logarithm of the parametrization. And so it's a gradient with respect to something other than cost, and that's, we'll come back to this point. But now let me go into the next slide, and show once more the implementation of the method for the discounted dynamic programming problem. So here z, the variable of optimization, is the trajectory, and we generate trajectories. And with this trajectory, we update the parameter Rk of the randomized the parameter of parameter. We update the parameterization of the randomized policies. So the cost function now is just the usual discounted infinite horizon cost, and z, of course, is this sequence here, and f of z is this sequence here. It's something that's random, and the problem is to minimize this expected value over r. And the policy gradient method involves this iteration. At Rk, generate a trajectory, calculate its cost, calculate this gradient expression, and then go to the next point, Rk plus 1. At that point, we calculate we generate another sample, Zk plus 1, calculate the gradient, calculate the cost, and go to Rk plus 2, and so on. And now this formula here, that's kind of mysterious, is given in a convenient form in the case of discounted dynamic programming problems. It's given by this expression here, which involves the transition probabilities of the problem, which are assumed known for this formula here, and the logarithm, the gradient of the logarithm of parametrization. But it is a stepwise summation over all the stages. Um is the mth control, the control of the mth stage. So all of this looks very formidable, but it's actually very easily implemented. That's one of the attractions of this method, that it can be implemented very easily. So what I'd like to do now is discuss some of the properties of this method and other related methods. Are there any questions?
Yeah, I had a couple of questions. Actually, I had a question about the initial optimization and training framework that was shown several slides back. I think you may have cleared it up in subsequent slides, but I just want to clarify for the optimization objective, if we use randomized policies, we'll also need to take another expectation with respect to actions that are distributed according to our policy, right?
Right, yeah, that's what this involved here.
Okay.
There's
So
there's the uncertainty, there's the transition probabilities, the inherent uncertainty in the problem, and then we randomize the policy so that adds additional uncertainty, and the expected value is with respect to the overall uncertainty, let's say.
Okay, so the initial objective function that was shown on, I think it was slide 14, was that just for deterministic problems? I think there is one expectation that's taken just with in respect to the initial state.
Let's see. Here?
Yeah, on the bottom.
On the bottom, yes.
Yeah.
No, that's not the expectation with respect to the uncertainty in that inherent in the transition probabilities, in the system dynamics, and also the uncertainty inherent in the randomized policies once we introduce randomized policies. This is expected value with respect to initial condition. In other words, there's one version of the problem where the initial condition is known, but what happens if you don't know the right initial condition? Then you modify this cost function to involve a weighted sum over initial conditions. So this expectation has nothing to do with transition probabilities or randomized policy. Does that make sense?
Yeah, it does. I was just trying to connect the dots because so the objective that you define later on isn't really connected with this. Because I was thinking like actually, if we condition the expectation on starting state, or for a given fixed starting state, the cost of that policy is still going to be random, just even due to the stochastic dynamics of the environment. So we would need to take those expectations over the full trajectory. So this isn't related to what you introduce in the next few slides.
Right, exactly. And okay. In fact, there are so many concepts that I'm rushing through that it's impossible to retain some of the details. But at some point, I mentioned that that we consider a fixed initial condition, okay, in which case this expectation does not come into play.
Okay. Yeah, that makes sense.
So let's go back because you said you had another question, right? Feel free to go through it. Let's go back to where we were.
On slide 21, what conditions will we need to hold in order to move from the discrete to the uncountably continuous case? Actually, I guess the title of the slide kind of gives away, you need to be able to reverse the order of the expectation, the gradient. So I guess my question is, in the context of our problem, when does that hold in the continuous space case?
Reversing the order of expectation and gradient is legitimate under very, very weak conditions. It's always true, essentially, for practical purposes. Because, expected values are weighted sum, and gradient of a sum is equal to the sum of the gradients, right? Yeah. So it's only under weird circumstances that only mathematicians care about that the reversal of the order is not legitimate. However, you may note this, what this line says here, we assume that this is a discrete distribution. Okay, if it's a continuous distribution, then There are all sorts of mathematical questions that have to do with taking this expectation, because it becomes an integral over some arbitrary spaces. So just to be on a safe side, when you're taking do these calculations, I have replaced, I have assumed a discrete distribution so that Z here is just a finite set, okay, rather than an infinite set. For our practical purposes, this is not really something to be concerned with.
Okay, yeah, that makes sense.
Okay, so all of this requires a lot of calculations that I'm skipping here, and the point that's worth retaining is that even though this algorithm is very complicated to write, it's extremely simple to program. All you need is have a parametrization of the randomized policies and be able to generate sample trajectories according to parametrization. You are the point RK that defines the policy, and you have all the stochastic description of the system, and then you can simulate a sample trajectory corresponding to RK. And then there's a nice and convenient formula, a stepwise formula, a summation formula that calculates this troublesome logarithm term. Looks almost like magic, but it's true, and you can find in many reinforcement learning sources a justification of this formula here. And so you are at RK, generate a random trajectory, generate the gradient of the logarithm, off you go to the next point with some step size. Of course, there's an awful lot of trickery that goes on here, making all this work. It's a daunting task. People will not focus very much on how difficult it is to make this method work. But indeed, it is not easy, but it's an offline method. You can experiment a lot with different parameters, and in the end, you may be able to obtain some decent policy this way. So let me go into the discussion about some of the practical aspects, the practical implementation aspects of this kind of method, which, as I said, is very popular. Implementation issues. Okay, some unusual aspects. It involves the cost function of the discounted problem, but not its gradient. The cost per stage does not have to be differentiable. So is this really a gradient method in the mold of what we know and love, like taking the gradient of the cost function? Well, it's not really. G may be non-differentiable. The problem may be, it may be non-differentiable. So you can't define gradients of the cost function. What this gradient trick does is define some random direction, which on the aggregate is a descent direction along which you minimize, you can decrease the cost function. But that's not the gradient direction. Several people have pointed this out, but the name policy gradient is so popular that it's impossible to reverse. In my opinion, it's somewhat a misnomer. Okay, here's another problem. You have a perfectly deterministic problem, potentially, yet you randomize it in order to be able to apply this methodology. So what you solve is a randomized version of the original. So if you get a convergence of the sequence RK into some R bar, then you will get a distribution that may not be atomic. Okay, you are interested in atomic distributions. So if you get a randomized policy in particular, you'll have to make it deterministic to apply it online. So that's another difficulty here. And then there are some of the usual implementation issues that have to do with approximations of various kinds in dynamic programming. How do you collect the trajectory samples to make sure that you're exploring the search space appropriately, that you span the space of trajectories sufficiently well? And how do you do it in the way that you strike a good compromise between exploration and optimization effort, convenience of implementation, and so on? These are issues that are similar but not identical with the exploration issues in approximation in value space and policy iteration. Then you recall that the cost calculation in the context of discounted dynamic programming involves the cost function of the problem. Zk is a trajectory, a state control trajectory, and this is random. So there's a lot of noise in the calculation of this sample. And then this noise enters into this formula. So this is a very, very noisy calculation. And now people have used a certain trick that tries to reduce the variance that's inherent in this formula, and that is to subtract a constant from f of zk. Now, what's happening? F of zk may involve some large parameters, and on top of those, some large values, and on top of that, some fine variations. So by subtracting a constant, you take out the constant values and you leave the finer variations, and this helps in the overall approximation process. So people have played with the use of baselines, which are constants that you subtract out of this f of zk. There's a certain calculation that shows that the choice of b does not matter. These iterations are in some sense equivalent. However, there's a more general idea which subsumes this idea here of baselines, and I want to describe it to you in the next slide. Okay, this is an old idea. It's called cost shaping. The idea is to transform the problem so that the noise is not so much a difficulty. So we take the original problem. We're talking now about discounted dynamic programming and its cost function, J stars of X. X is the initial condition. J star is the optimal cost function. And you have some function, any function, some known function, V sub X, and you subtract it out of J star. So in some sense, you do a translation of J star with this V sub X function. Perhaps there's a large constant involved here in this J star, and this could be something that approximates its constant. You change its shape, and from J star, you make it J hat. And then you make a change in the cost per stage. And this is the cost per stage at state X going to state Y under the influence of U. And you add this term here and subtract this term. Subtract V sub X, the state from which you start, and alpha V sub Y, you add that where Y is a state where you end up with. So let's introduce this J hat and G hat and take the Bellman equation from the original problem. Okay, so let's look at this equation. If you use the definition of J hat and the definition of G hat, then this equation is identical to the Bellman equation of the original problem. So the original problem's Bellman equation, J star equals mean sum of the pxy of u g plus alpha J star, can be written in this form. But now if you look at this, it's another Bellman equation where J hat is the cost and G hat is the cost per stage. So if you introduce another problem where the cost per stage is G hat in place of G, then J hat is the optimal cost of that problem. That's what this bullet says. J hat, the translated version of J star, is the optimal cost of another problem, which is simply the same as the original problem, except that the cost per stage has been changed, and from G, it has become G hat. So we can play around with different V functions and get equivalent versions of the discounted problem. Now, what do we gain from this? Well, if you're interested in an exact solution, the optimal policies of this reformulated problem are exactly the same as the optimal policy of the original problem. So nothing will change if you're interested in solving this problem or the original problem exactly. You're going to get the same thing. However, this reformulated problem may have a more favorable shape for approximation, okay? Once we consider approximation methods, be they approximation in value space and policy duration, or being policy gradient, or random search, or other methods, they will give you different results from the J hat problem than for the original J star problem. And it turns out that if you choose this V close to J star, you can subtract out a big portion of J star that may be causing a lot of trouble in the sense of swamping out fine detail variations of J star. Now, you may remember this or you may not remember this because it was several lectures back. In lecture 8, we talked about advantage updating. And advantage updating is Q learning, but with Q factor differences, which are called advantages, as opposed to Q factors. And by doing this change to advantage updating, I gave an example there and I discussed how approximation methods can deal a lot with this, small scale variations in J star or the Q factors and so on. Now, what does this have to do with baselines? Where this V sub x are just state-dependent baselines. If you look at this formula here, if you introduce a V here, that's going to be your state-dependent baseline. And basically, you will be approximating a problem that's equivalent. It just is going to involve a cost function, which is J hat over J star. There's so many details here, and I can't really go into this. What I want to impress on you, however, there's an awful lot of methodology of these policy gradient method that revolves around these baselines. And people talk about various tricks for selecting good baselines and how you use them in the context of policy gradient methods or policy gradient methods that are modified in some sensible way. And an awful lot of the methodology of policy gradient methods revolves around this type of techniques. Are there any questions about this slide?
Yeah, I had a question for, so you said you didn't want to get into it. I guess I was going to first ask, like, how do we know, is there some kind of optimal choice for the baseline? And two, when you said, you know, that we can use a state-dependent baseline and plug it back in to what we had on the previous slide, I'm kind of confused a little bit on that because everything there is defined in terms of trajectories. So if we did that, would we just be using the state corresponding to the start of that trajectory, or how would that work?
Okay, your second question first. The way you do it is after you have V, and we'll talk about how you get V. You simply change the cost per stage, and that's all. That's all you have to do in the previous formula, in the previous slide, in this slide here. Okay, actually, we should go to this slide here. instead of G, you use G hat. And that's all you need to do.
Okay, yeah, I see it. Yeah.
Okay. So that's relatively simple, but the question of how do you choose the baseline is very tricky. One rationale, the most common rationale, I think, argues for choosing V to be close to J star, okay? So the range of this J hat here is relatively small, and which is convenient, it's useful for approximations. So suppose that you have some policy, some good policy, okay? You know some policy that is relatively good, and you can simulate that policy, and you can get a cost function of that policy approximately through training perhaps of a neural network if you wish, okay? Generate a lot of cost samples using this policy and fit a neural network to approximate the cost function of that policy. And you use that as a baseline. Of course, this takes a lot of work because you have to work first to obtain a good baseline, and then you have to work again to train the policy. But all of this is offline. All of this is done offline. So you can work for hours and days and weeks if you wish, if you're so motivated. So that's one possibility for V. Does that answer your question?
Yeah, it does. I had a quick related question for the content on the previous slide as well. Is there any effect on if we use like a mini batch? If say we're in the case where we were implementing this through a neural network, can we use like a mini batch instead to try to reduce the variance on the gradients?
Most definitely, yes.
Okay. Because you're saying like right now we're just using the one trajectory sample.
Right. This is the simplest way to describe this method, but you can take lots of trajectories and then take the average of those in this formula. Okay.
Yeah, I'm kind of curious.
Take the expected value over the samples that you collect, and that reduces the variance. Yes.
Okay, and then also I was curious about like adaptive learning rates. So the two things I was thinking in terms of how we could try to address that problem in terms of if we implemented this through a neural network is, you know, batch size, obviously, and then does adapting the learning rate help us at all?
Okay, by learning rate, you're using the term learning rate, with which
the gamma K.
You're familiar, okay? I don't use this term learning rate, I use the term step size. You're talking about gamma K either way. And how do you choose the step size? Well, neural network programs will do it for you. You use some heuristic rules. You may have to play around with them, but this is another weakness of this method. How do you pick the step size? If you don't have a program to tell you how to do it, which it's not clear that the program knows what it's doing actually. But anyway, this is a weakness. You have to play around with different ways to choose the step size. And the theoretical possibility is to have this gamma K go down to zero. It's a diminishing step size. And it has to go to zero at a certain rate. And that rate is O of 1 over K. So, okay, so you reduce the step size according to the sequence 1 over K. But people rarely use that. People use complicated rules that diminish the step size. For example, they keep it constant for a while, and then they drop it again, and then they don't reduce it beyond a certain floor. That's also common. And how do you choose the parameters of this kind of step size rule is kind of opaque. You can't really tell. All you have is that theoretically, if the step size is diminishing and it's diminishing at the general rate of 1 over K, then you're covered by theory as much as you're going to get covered. The remainder is heuristics and experimentation. So that's all I can say about the learning rate.
Okay, thank you. Yeah.
Any other questions? By the way, the issues here in this policy gradient methods, including the step size issue, and also the mini batching, how many gradients do you batch together? All of this is part and parcel of the general methodology of incremental gradient methods. In discussing incremental gradient methods and the backpropagation method that underlies the training of neural networks, we described as if you do this with a single sample, but it's possible to group samples together and obtain an approximate gradient that has that averages over multiple samples and has less of a variance. All of this is part and parcel of the things that people do in practice. And as I said, it's all a difficult methodology to work with, but everything is done online, and there's a lot of software help to that is available. So all in all, people have had quite a bit of success with these incremental methods. Now let me go into the next slide about policy gradient methods. What do you do with a policy gradient method? Well, you train its parameters, the parameters of the cost function, and then you have a fixed policy that you apply online. But there's a general difficulty with somehow obtaining some policy through offline training and then try it online on your system. This is the kind of methodology that's all training and no play. All your work is done in training, and then you use what you have obtained from the training online. You have this policy, you observe the state, you apply the corresponding control instantly. That's very good because you compute controls very fast online, and therefore you can deal with very fast timescales of system control. On the other hand, this could also be very bad. For example, this type of policy gradient method, if you take the result and you apply it on your system, it has no way to adapt to changes in the system's parameters. In other words, it may be good for the parameters that it has seen, but once the problem's parameters change, then it's lost. It doesn't do sensible things necessarily. So if you have an adaptive control context where the system parameters change with time, then a policy gradient method is not very good because it will going to encounter a system that it has not met before, okay, through these parameter changes. Moreover, one of the disadvantages of using a fixed policy online is that you do not get the benefit of online look-ahead minimization and rollout. Even if the system parameters do not change, through one-step or multi-step minimization, through one-step or multi-step look-ahead minimization, you get the benefits of rollout. You get a policy that is better, is improved over the policy that you started. And in particular, rollout with this fixed policy may work much better than the policy itself. And the best example I can think of is AlphaZero. You remember that AlphaZero, through training, very vigorous training with lots of parallel computation hardware, yields a position evaluator, which is like an approximate cost function, and also trains a policy network, a policy to play online. And this policy is used during online play, but in conjunction with multi-step look ahead and rollout. So if AlphaZero were to take the the policy network, the policy obtained from the deep neural network obtained through offline training, then it would play not very impressively. It may play like a strong player, but nowhere near the phenomenal level of play that is capable of playing through multi-step look ahead and approximation in value space. So bear that in mind. It is using a fixed policy does not take advantage of this rollout bump in performance, and also cannot deal very well with adaptive control situations. So here's an alternative use of approximation in policy space, which is like what is done in AlphaZero. It can provide a base policy to be used in truncated rollout and multi-step look ahead, including possibly Monte Carlo tree search. And this is similar to what is done in AlphaZero. So this leads to a view of reinforcement learning where approximation in value space is the dominant method, and approximation in policy space is used in a subsidiary role to enhance and implement various aspects of approximation in value space, obtain some base policy to use in multi-step look ahead, obtain some cost function approximation to use at the end of the approximation in value space, and so on. So this kind of argument makes the case that you should be looking at approximation in value space and integrate approximation in policy space as you need to facilitate the implementation of the value space method. Okay, are there any questions here?
I'm just kind of curious if you've seen any papers where people have successfully found good policies using evolutionary methods.
Okay, evolutionary methods are a form of random search, okay? Right. You could use, in place of the cross-entropy method that I discussed, you could use an evolutionary algorithm. Both of these methods come under the general category of local search methods. And the general pattern of these local search methods is that they are iterative, and from one iteration to the next, you construct a neighborhood of points within which you search, always looking for cost reduction. So you could use the cross-entropy method, but you could also use in its place genetic algorithm or evolutionary algorithm, or you could use some other kind of random search method. However, now people have used the evolutionary algorithms. There's a literature, there's a lot of, it's not a very popular method in this context, but people have used it. So coming back to your original question, if I know of any references, I think there have been quite a few references, in fact, but they have not been, as far as I can tell, they have not made as much of an impression as the papers that use either the cross-entropy method or methods that are based on policy gradients.
Okay, I see.
Okay, I think we've reached the end of this video. And policy gradients and approximation policy space are a vast subject, a very popular one. And and we covered it in very quickly, because our main subject had been approximation in value space, the connection with Newton's method that you saw a reference on the last slide. and this type of algorithm. This lecture is based on material that is in my 2019 reinforcement learning book. And there you find the explanation of all these complicated formulas on calculating the gradient gradient of the logarithm of the distribution and various other aspects of the implementation. So what I'd like to do now is, well, conclude the lecture. Excuse me. Too many videos, too many slides. Okay, so where are we in this class? We have only one class that will cover new material, and that will cover aggregation next week. And aggregation is a methodology to train offlines, an offline method, to train a cost function approximation that could be used in approximation in value space. And there is a video lecture from last year's class, which I will use next week. And then on lecture 13, we are going to do an overview of the entire course, and then we will be done. And after that, we will have the presentation of the projects and a discussion of a general discussion of various aspects of the course within that context of projects. So that's it for today, and we'll see you next week.